next talk is by Phillip Burke from UCD, and he's going to tell us about his recently accepted work, new non-Hermitian numerical group, non-Hermitian numerical renormalization group.
Okay, hey everybody, like Shane said, my name is Phil, and it's always nice to be here in Dias. I'm a postdoc at UCD, I'm working with Andrew Mitchell, and today I'm talking about the non-Hermitian numerical renormalization group. The last thing can be shortened to NRG, just for saving time. And I will use it to solve the non-Hermitian Kondo model. Okay? And this work I'll talk about today is based on this publication on arXiv, which has just recently been accepted at PRL. So you can keep an eye out for that. And it's also funded by research grants, just to point that out. Okay. So, just in order of the talk, I will first introduce quantum maturity models and the regular NRG, because I'll be talking about the non-Hermitian version of NRG. I'm not going to assume everyone's familiar with it. And then I'll do a brief overview of non-Hermitian Hamiltonians, and I'll also assume not everyone's familiar with non-Hermitian Hamiltonians. And then we'll get to the actual crux of the talk, which is non-Hermitian NRG, and using it to solve the non-Hermitian Kondo model. Okay? And maybe if we have time, we'll get to the solution of a different model other than the regular model. Okay? So, NRG, we use to solve these quantum impurity problems. Some kind of paradigmatic examples of it are the Kondo model or the Anderson impurity model. Some of you may have heard of them. A sort of illustration of what they can look like is here on the right, where you have this, what I call the quantum dot, which might be an experiment. That's just your impurity, and it's coupled to some bath. And that bath is, could be a fermionic lead in a lab, but they don't necessarily have to be fermions, it could also be bosons or spins or something like that. The idea is you have a single impurity quantum, and it's coupled to some massive bath. It's meant to be a continuum. Okay. So, NRG method was developed by Wilson back in 1975 to solve these kind of problems. And it's very general in that you just need to model your impurity and pick some kind of bath, and then you throw energy at it. It's been solved. And what it does is it captures the low energy physics, so it specifically focuses on low temperature, low energy parts of the system. And it includes these many body correlations that come from this interacting model. So this is an interacting, okay? But one caveat is that for energy, your bath has to be a non-interacting. So this should be like a sea of free fermions or something. Okay. So how does the energy method actually work? I'll just do a kind of a high-level outline of it. So you take this continuum bath and you want to map it to a discrete bath. Okay. So you're discretizing your bath, but you do it in a special way where you do it logarithmically. So instead of just taking this, say flat band density states for like a metal or something, instead of just breaking it up into evenly spaced windows, you take them where they decrease as you go closer and closer to zero energy. That's what's happening here, right? So instead of having just regular spaced windows, they're getting narrower and narrower, and as you get to zero energy, you have this super fine grid. Okay, and this is your logarithmic discretization that you want to carry out. Okay, so then you take this discrete bath and you map it to a type binding chain. We're talking about the 1D chain, right? And then I've illustrated down here in the bottom right. So you have your impurity, this R point here, and you couple it to the first side of your chain, and then another side of the chain, and so on, so on. That extends infinitely in one direction. Okay, and then the couplings between these Wilson side chains are these TNs, and you want them to decay exponentially as you move further and further down the chain. Okay, so this is Wilson's construction, and hence it's usually referred to as a Wilson chain. Okay, so that's the setup, sort of what you need to do to start doing NRG. Then what you're actually doing is then iteratively constructing this chain that we now have and solving it at every single iteration. Okay, so what you do is you start off with just your impurity, or maybe just the impurity on the first side of your chain, and you add on a new site, and then you solve your new Hamiltonian, and then you add on another site, and then you solve your new Hamiltonian, and you do that ad infinitum. Okay, so you keep on making the system bigger and then solving it. But obviously, you'd want to do that, infinitely. So you map your actual infinite system with this massive continuum bath. Obviously, this is numerical renormalization group. We cannot do that. We cannot map some infinite system on our computer. So what you do instead is you start truncating. So we're interested in the low energy physics, and by Wilson's construction, you get this nice energy separation. This logarithmically discretized path, and also this these exponentially decaying TNs mean that when you get this nice energy scale separation between low energy states and high energy states, which means that at some point, obviously, your Hamiltonian is going to be too big to store in a computer and solve it. So at some point, we're going to stop. We're going to go, okay, I only want to keep 1,000 eigenstates and use those to construct the next Hamiltonian. I'm going to throw away the rest. Okay, so that's your truncation step in this NRG process. That allows you to keep going to further and further sites in this Wilson chain. Okay, so then the process is now add on a site, diagonalize it, only keep 1,000 of the eigenstates, throw the rest away, and then use those to construct the next Hamiltonian by adding on another side, and you solve it, and then you just repeat. Okay? And the idea is that this provides an effective Hamiltonian, which provides accurate spectrum, the accurate spectrum for the full system, but only for the low energy states. So you've obviously truncated, you're no longer interested in the high energy states, but it will eventually provide a very nice effective Hamiltonian for those low energy states, low temperature states. Okay, obviously how accurate it is depends on the number of states you keep. Obviously, if you're only going to keep like 100 states, it's not going to be very accurate for the full system. And so usually this is on the order of like a few thousand, which obviously does fit on a computer. Okay, and also depends on how many iterations. Obviously, if you only do a couple of iterations, you're not actually representative of the full system. Okay, so this is a very broad overview of what energy does. So it's just this mapping some discrete path and this constructs Wilson chain, and then the actual process is just this iterative construct, diagonalize, throw away, construct, diagonalize, throw away. So that's energy. So that's how you do it. What's it useful for? Obviously, it generates a spectrum because every single step you have a Hamiltonian and you're calculating eigenvalues. And then that's, at the end, those eigenvalues are meant to be representative of your full system. And with those, you can do thermodynamic quantities like entropy, obviously. And you also get to observe this renormalization group flow between fixed points. So going from some initial Hamiltonian and it eventually relaxes to some final Hamiltonian where every single step, that Hamiltonian isn't actually changing anymore, essentially. It's your fixed point. And you can observe the eigenvalues, like the output of the energy, flowing from one kind of fixed point to that final fixed point. We'll show an example of it when we actually get to a real model in a few minutes. And it's also nice because it's super general. It applies to lots of general impurity problems like the Kondo, the Anderson impurity, and their variations where you have multiple impurities, there are multiple baths, that kind of thing. And it also, the bath itself can have different density states. The example I showed is just this flat band density of states. We can use lots of other ones. Energy is a very general method. Okay. It also has some extensions for computing dynamical quantities. That's like full density matrix energy. If you want to calculate spectral functions or Green's functions, that kind of thing. Okay. So that's energy, nice and powerful. But what if your system is now coupled to an environment? So what if your impurity has some dissipation into an environment? What if your lead has some dissipation into an environment? That kind of thing. Okay. This is now an open quantum system. So what if you want to solve a quantum impurity problem that's now open? You want to include some effects of interference or dissipation or something like that. Okay. So open quantum systems like these can actually be effectively described by non-Hermitian Hamiltonians. So that's going to be described in a minute. But one thing that's good, we now have a system described by a Hamiltonian, and energy is kind of based on Hamiltonians. But normal energy in its construction assumes your system is described by a Hermitian Hamiltonian. Okay? So what we need to solve these kind of problems is a non-Hermitian version of energy, a non-Hermitian numerical renormalization. Okay. So before I jump into anything else, any questions with the setup, the preamble? Okay, you're happy? Okay, so non-Hermitian Hamiltonians, this is a slightly technical slide. It's just going to be numbers and words, sorry in advance, but it's brief. Just I want to make sure everyone knows what a non-Hermitian Hamiltonian is. So obviously, as the name suggests, it just means H dagger is not H, it's non-Hermitian. And that generally implies that you have a complex spectrum, so complex eigenvalues. It's not always the case, this doesn't have to be the case, but it is generally the case. We won't talk about specific cases where it's not true. And one of the caveats is that you have left and right eigenstates. So normally in regular Hermitian quantum mechanics, obviously you always have left and right eigenstates, but they're equivalent in the Hermitian case. Whereas here, they're no longer equivalent. You have two separate bases, and they're not equivalent to each other. Also, they do not form an orthonormal basis for your Hamiltonian, okay, on their own. But what you can have is what's called bi-orthonormality. So you have two bases, but they can actually make up one kind of complete basis when you join them together. So normally when you have these two bases, they're actually bi-orthogonal. They're not necessarily normalized. And if you want to learn more about that, there's this paper by Brody in 2014 about bi-orthogonal quantum mechanics. Okay. So they're generally bi-orthogonal, and if you take one eigenstate from the left basis, there's only one matching eigenstate in the right basis, which is not orthogonal. Okay. They won't necessarily be normalized, but then you can just manually do the normalization like so. Okay. And then the two bases, now that you've normalized them, bi-normalized them, you can then construct your Hamiltonian and diagonalize. Okay, so then we want to do energy, which just involves this construction and diagonalization. And the main thing you just need to take into account is when you're doing the diagonalization, you need to get your left eigenstates and your right eigenstates. I mean, if you do Python and you ask it to give you eigenstates, by default, it just gives you the right eigenstates. Okay, so just when you're doing this numerically, you need to calculate left and right, and then when you're doing the construction, you just need to use both. Okay, and like I said, you have some complex eigenvalues. It's also just the identity operator. Use both right and left. Okay, construct this projection operator. Don't worry about it. Like I said, this paraphagalization thing isn't always there. You would kind of have to have non-degenerate spectrum. You can kind of avoid these degeneracies by just doing this energy process within symmetry sectors. So use quantum numbers for diagonalization and construction. Okay. All right. So for any more exhaustive details, I'll refer to the paper. It's not very lightning. It's very technical. But like I said, the construction of diagonalization, the main thing is just complex eigenvalues, left and right eigenstates, and then you sort of proceed as normal. Okay. But there's one last step in our energy process, and that's the truncation step. So we're always interested in keeping some like set amount of low energy states. Obviously, in the Hermitian case of energy, you have a real spectrum, so it's quite straightforward. It's like a number line. You're like, okay, I want to keep the lowest, like 1,000. I just look to the left, like most 1,000 eigenstates, and keep those. But we now have a complex spectrum. So what do you do in the case of a complex spectrum? What are the ground state energies say? So do we want to keep like the eigenstates with the lowest real value or with the lowest magnitude? What do we pick? Okay, so we'll just talk about this for a second. So this is the complex spectrum. This is some real non-Hermitian Hamiltonian. I've diagonalized it and I've plotted its eigenvalues in real imaginary plane. So this is for a type binding chain with asymmetric hopping, which happens to be a non-Hermitian Hamiltonian. The actual system doesn't matter. This is just as an example. And what I've done here, these black points, which hopefully you can discern from the red points, are the solution to the exact like 2 to the L to the L Hamiltonian. Okay, and I want to just point out that you can still construct the many body states of a non-interacting non-Hermitian system from a single particle. These red points, which you probably can't see just because of the projector and the screen, but they're actually lying on top of each other, which is obviously why they're difficult to see. That's a good thing. We want to be able to construct all our many body states from single particles. So that's what these red points are. These are just those ones constructed from single particles. Okay, but the question is, what's the ground state in this spectrum? Like which one of these points do you identify as the ground state? There's obviously a few obvious choices. You could pick the one with the lowest real component, this leftmost one, kind of like our number line is just the one most to the left. You could pick the one in the dead center, the one with the lowest magnitude, so close to 0. You could pick the one in the most southwest part of the plane. If you think of like a 2D version of the 1D problem, it's negative in most negative in both directions. Or you could pick the most imaginary one. There's a bunch of different ways you can think of doing it. Okay. I don't expect you to answer the question. There isn't really an answer to the question. There's just conventions. Like in the non-Hermitian literature, there isn't necessarily one consensus of this is the ground state. Okay, there are some general conventions which we'll see in a second. But in energy, we want the lowest energy states. So the question really is what portion of the spectrum would we pick at each step to keep or throw away? Okay, and will it make a difference? Will it affect our energy process? Will it make it like accurate? Will it break it? We need to see. So let's just actually take some of these examples and just use it with energy and see if it works. Okay, so let's go to a real system now. This is now a non-Hermitian impurity system, so it's similar to before. You have some impurity, which could be on a dot. It's coupled to some bath, and you're allowing this non-hermiticity to be introduced either on the dot or through the coupling or on the bath itself. Okay, this can be modeled. This is just an Anderson impurity model. So your dot here is actually a fermionic degree of freedom that can host spin up and spin down and interact with each other. And we're going to assume that the bath is some flat band density states. Okay, so this is the setup. Now we're actually going to turn off the impurity altogether. Okay, we want it to disconnect from the bath so that we can solve it exactly, and then we can test these truncation methods to see which actually works. So we can compare our energy results with an exact solution. Okay. What I've done here is I've basically disconnected the hybridization. I've turned off the interaction on the fermionic degree of freedom itself, and I've basically just totally polarized the spin in one direction, so that it basically has no contribution to the physics of the spectrum whatsoever. Okay, and then your Anderson grid model just becomes something that's polarized and not going to do anything, and then just your non-interacting bath. Okay, so that's now this is still just the Anderson grid model without the impurity, of course. And now I'm going to introduce some dissipative potentials on the bath. So now what you're basically left with is a type binding chain with a bunch of imaginary potentials. Okay, so it's a non-interacting, non-Hermitian system that we can solve exactly. And we can also solve with energy. Okay, so it just allows us to give a comparison for energy with something that we know exactly the solution to. Okay, so it's just a diagram of what we have again. So now I'm plotting the exact solution, these black points, which again are hard to see because they're on top of each other. So that's a good thing they're on top of each other. And And the black points here are the exact solution. And on the top here, I'm plotting the results of using the lowest real truncation scheme. The bottom is a different truncation scheme of using the lowest magnitude. At this point, it doesn't matter about the truncation schemes, it's not truncating. Okay, so these are just all the eigenvalues for like two particular steps of energy. And what we see here is actually, like I said, they match up perfectly, which is why it's kind of hard to discern the fact that they're on top of each other. So this is good because it means our energy, first of all, is working so far without any truncation. The non-Hermitian energy method produces the exact results that you get from diagonalization. Okay, but now we want to do a truncation. So that's the whole point of this sort of step, is you want to see which truncation scheme works at producing the correct eigenvalues. Okay, so just focusing on using the lowest real components first. So this, I'm picking that leftmost point in that Argand plane. Okay, I'm going to use that as our ground state and just pick the next, 1,000 states if you order them by this lowest real component. And as you see in this first, third plot, we'll say, we're now only generating like roughly half the spectrum. So we've thrown away some amount. We're only keeping some set amount, which is like 800 or something. And you see they're still matching up perfectly, but we're just not getting them all. So that's energy. That's how it works. You're only keeping some low energy states. And likewise, truncating again, we're only generating less of the spectrum, but again, it's perfectly accurate. It's working really well, and it's just generating the eigenstates in the system that have the lowest real components. Okay, so it's nice to see that's working, at least with this truncation scheme. Whereas if we go to the lowest magnitude truncation scheme, so like always focusing on those that are closest to zero in that complex plane, you actually see it works equally well. So these eigenvalues are also matching up perfectly. It's actually just generating a different component of the spectrum. So instead of generating the lowest real components, it's generating the lowest magnitude. These are closest to zero, like the 0, 0 point, the origin of the plane, whereas these are always just with the lowest real component. Okay.
I don't understand what you're iterating.
So at every single step, we're adding on one side to the chain. And that generates a new Hamiltonian. And then you diagonalize that.
A chain.
Yes, this is already a chain. Sorry. And then so this would be like the impurity, and then with 6 sides of your chain added on to it. And the fermions, so it grows by a factor of 4 every single time you add on a new step. Okay. All right. So this is nice because now we've kind of confirmed that our energy method is working, it matches up with the exact solution. And it also means that the truncation scheme sort of the method is somewhat indifferent in its accuracy. It just produces different components of the spectrum. Okay. So which one we're going to pick? We're actually going to just end up using this top one, this lowest real component. First of all, because if we want to look at like the Hermitian limit of some model, it'll obviously be much easier to match up with the eigenvalues sort of in the same manner in that limit. And also it's somewhat conventional in the non-Hermitian literature that you take the lowest real component, but also because it's easier to match up with the real Hermitian case. Okay, so from now on we're going to use this top truncation scheme, first of all because it seems to be somewhat indifferent, but also it'll make it easier to match up to the Hermitian case. Okay, this is all non-interacting. Let's look at an actual interacting non-Hermitian problem. Okay. So the Kondo model, kind of the paradigm in like these quantum impurity models, where people saw like the Kondo effect and things like that. So it's just given by this Hamiltonian here. So you have your usual bath, and then there's just some spin coupling between your impurity is now just a single spin degree of freedom, it's only like an electron, and your interaction in the system is purely between the spin and then the spin on the first overall of your bath. Okay, so this is now the setup. This is the Hermitian one for now, which obviously has been studied loads in the past. I mean, energy itself is sort of developed to solve this Kondo model, and it's known that there are two sort of phases in the model. One where you have what's called a local moment fixed point, strong coupling fixed point. So here what I'm showing is output of actual like energy. This is just normal energy for now, because this is our Hermitian model. This is basically Wilson's results, just replotted by me. So on the left here, you have zero coupling between the spin and the bath, and you get what's called the local moment regime, where basically your spin is just totally free to do whatever it wants, and your bath is just a normal type binding chain. Okay, so just a normal, well, it has these exponentially decaying couplings, but it's just a type binding chain with some specific couplings. So you see what you're observing here is the flow. So this is like some set of eigenvalues on the y-axis plotted versus every single iteration. So to start here, you just have some like like an impurity on one side of the chain, and you keep adding one on every single iteration. So that's what's going on the x-axis here, is increasing the length of that chain. And what you see is actually the eigenvalue structure for just your impurity and like the bath side doesn't change for the whole system. So the actual like the full eigenvalue spectrum for the whole bath is the same for the as in its structure is the same for just your impurity and your first orbital. This local moment structure, as it's called. Okay. Whereas once you turn on any finite coupling, so as j is greater than 0, your impurity and your bath are now coupled together, and you get this new structure in the end. This is what's called strong coupling fixed point. Okay. What's nice in this one is actually you actually see this renormalization could flow from what is roughly the local moment fixed point of your just impurity coupled, just your impurity with like one side. You observe its flow to this final strong coupling fixed point, which is then representative of what the actual system is, where you have this continuous path at your single impurity. Okay, so this, like I said, this is some known result. This is just regular Hermitian Kondo, and this is resolved by NG or like that kind of thing. So let's make this non-Hermitian. This is boring. It's just known. Okay. So the non-Hermitian Kondo model. So what we've done here is now make our J complex. Okay, and that makes the system non-Hermitian. This was sort of introduced first in the context of like some ultra cold atom setup by these people, Nakagawa and some others, in this PRL in 2018. And this complex coupling J was meant to be introduced some two-body loss between basically your impurity and your first site on your chain. Basically, they're coupled, but there's also loss to your environment modeled here. Okay, so the effective Hamiltonian, which is non-Hermitian, is actually derived from like full Dinblad. So it's an accurate description of the system. And what they saw was that the two fixed points from the Hermitian model persisted in this model. So they used some Bethe-Ansatz method, some approximation about linearity and stuff like that. And they came up with some perturbative solution. And then what they saw was the same two fixed points. There was some possibility of a third fixed point that was reported earlier this year by Cattle and some others. But basically all the studies on this non-Hermitian Kondo model so far have been perturbative or the use of approximate methods. Okay. Whereas our non-Hermitian NRG method is non-perturbative, and you can go way into the strong coupling regimes and see what the phase diagram looks like. Okay. So just first of all, the kind of flow diagrams you actually see. We also observe the two fixed points from the Hermitian model. So just on the top here, plotting the same fixed points as before, just unfortunately in reverse order. So here's the strong coupling regime with a similar kind of structure. You see the flow from roughly local moment to strong coupling, and then the local moment sort of goes local moment a tiny bit away from it, and then back to local moment. So what I'm plotting here again is n versus the top here is just real components of your eigenvalues. But the fixed points are emergent Hermitian fixed points. And I call them emergent because in the middle there's this sort of complex flow. On the bottom here is the imaginary components of these corresponding eigenvalues. And you see that in the middle, sort of near this crossover, these imaginary components really grow as this flow happens, but then eventually they die off again. You end up back with just purely real eigenvalues. Okay, so that's why we call them these emergent Hermitian fixed points. So even though it's a non-Hermitian model, you end up back with these real fixed points in the phase diagram. Okay, so these are just two examples of what the flow diagrams look like, but we can actually look at the whole phase diagram now. Okay, so here is our newly uncovered full phase diagram for the non-Hermitian Kondo. So this orange region here is where you get the local moment regime, okay? And where this blue line, this blue region here, which looks almost white on this diagram, is the strong coupling regime. Okay? So obviously in the real case, you would just have the 0 point is your local moment, and anything above 0 is your strong coupling regime. Okay? So the first thing to focus on here is this inset. So the original paper by Nakagawa and others, they used this Bethe-Ansatz with some approximations to go into some perturbative regime, and they calculated this red line in this phase diagram, and they said that it should be accurate up to a magnitude of about 0.25 in the phase diagram. And we see our result, this black line that separates the two phases, matches up really well in sort of the regime where you expect it to work. It's not in this like perturbative regime. Okay, because like I said, our non-Hermitian energy results can go way beyond that, and can cover the whole phase diagram. So this region is here, that inset. Okay, so we can cover the whole thing. So in this phase diagram, what we're really observing is the interplay of dissipation and correlations. We still have this strongly interacting system, and we're observing the interplay with dissipation going on. So first of all, you can get this local moment regime, even with some finite coupling, like some finite real coupling JOR. So in the normal phase diagram, for the Hermitian case, obviously, once you have any coupling, you're stuck in the strong coupling regime. Okay. Whereas now we see if you pick a point here like 0.4. Obviously, when it's Hermitian, you're in the strong coupling, you slowly turn on your dissipation, and you move up until you hit the local moment regime. So at some point, you introduce enough dissipation into your system, and it breaks that coupling enough to allow you to get the local moment regime again. Okay? But if you have too strong a real coupling, if you go way beyond up to here, actually the Kondo effect just totally dominates, and no matter how much dissipation you put in, you're just stuck in the strong coupling regime. Okay? One thing that's slightly interesting is that if you keep going up in dissipation, if you keep going up this y-axis, you'll be in the local moment regime, and then you return to the strong coupling regime. So there's this re-entrant strong coupling behavior. So one explanation to this is that you can get what's called dissipation-induced localization, whereby when your dissipation is much stronger than the bandwidth of your system, basically it just induces localization on those two sites. Okay, well, two sites in this case because it's this two-body coupling between two spins. Okay, so basically your coupling is that your dissipation is so strong, you're localizing that first spin on the bath with the impurity, and then that means you're basically screening out one side of your bath, and that bath is now just a free Wilson chain with one side removed, which is actually just a strong coupling fixed point again. So that's basically why you get this re-entry behavior, just because of this localization that occurs. Okay, so this is the full phase diagram, totally new and uncovered for the non-Hermitian Kondo model, and it goes way beyond the perturbative region.
So you're also showing the beta ansatz solution.
So this red line here is the beta ansatz solution. But the beta ansatz solution
compared to your.
So it compares really well in the regime where they said it will work well. So I think in this paper they make some assumption about linearity of the dispersion relation. They say that's only true in this regime where the magnitude of J is less than or equal to about a quarter. So in that regime where it's predicted to be correct, our result matches it pretty well. So that's this red line here is their result. And I guess up to here is where they expect it to be accurate. And our result matches that. So that's also a nice test, I guess.
All right, so your result is no better than theirs.
Well, our result is better because we can go way beyond this. I mean, because they only expect their results to be accurate to about here. Whereas we expect our results to be accurate everywhere. And then we do calculate them with the error.
But nevertheless, it doesn't include the beta.
Well, because they think their meta that's going to be wrong after this. That's why there's this difference basically. Because they're saying their result is only true up to here, and afterwards it doesn't really mean anything because their assumptions they make are no longer true in this regime. Whereas we don't make any assumptions, so ours is expected to be accurate the whole time.
So the beta ansatz is not exact in the non-Hermitian case.
It's correct in the perturbative regime. Their beta ansatz result that they have. Does that make sense?
No, that's not clear because the beta ansatz is exact, but
I
only know it for the Hermitian case.
So in their I mean the paper I guess will explain it better than I will, but they make some assumptions to apply the beta ansatz, and those assumptions break down beyond some coupling regime. Sorry, I can't explain that more on beta ansatz. Okay, how are we doing on time before I either end this talk or?
4 minutes, yeah.
4 minutes, okay.
Thank you, sir. So, just on the space diagram, you mentioned that the truncation you did, you chose the smallest field terms.
Yeah.
If you choose some other choice, you basically still get the same space diagram.
Yeah.
Independent.
You know, it's independent. So it's just harder to match up with like, oh, this is you have to reorder them in a specific way to be able to find that you're in the local moment regime with strong.
And it's obvious that it should be independent.
Well, it's still generate. I mean, I guess if you truncate like in a totally bizarre way, like you start truncating by keeping the highest energy states, then you're generating, you're going to have to somehow identify the local moment structure from the high energy states instead of the low energy states. So I guess at some point it kind of becomes unsensible to use some other truncations. So you sort of have to identify the structure in a certain region.
But it's like if Ji is very large, there's obvious flux with flux truncation. I mean, it's a two question right now. What is the physical truncation?
Yes, so I guess my answer is from the things we have tested, that using sort of reasonable truncation schemes like lowest real, lowest magnitude, where you can mix kind of combination of two, they seem to produce the same phase diagram. But I guess if you start truncating by something else, like lowest imaginary or something, then you start ordering them in weird ways. You might be mixing what would traditionally be called high energy or low energy.
It's fun. In the we had a flow of this, the flows. Are those flows also relatively? I mean, I guess they'll quantitatively change if you change, I guess, the agency, but they're qualitatively the same.
Yeah, I mean, the exact flows might change slightly because I guess because you're sorting them by some method, they might slightly shift around, but the overall quantitative behavior is the same. You end up with this, strong coupling fixed point, local fixed point, and where they belong in that phase diagram.
They still look at emergent. They still look at emergent.
Yeah. So there's almost always this growth. There just always is this growth in the middle in the imaginary components. And they go. We're sort of thinking that the critical point itself, like exactly at some critical coupling, the fixed point might be non-Hermitian. You might have complex eigenvalues, and that's why these are growing so much. But obviously, we never actually touched that exactly. Okay, so because we have a few more minutes to change it, let's test it on the non-trivial system. So like beta ansatz applies to the Kondo model. What about something that the beta ansatz can't do? So we're going to look at a non-integrable system. So we have a nonlinear density of states. That's kind of has to assume for these Kondo models. So we're going to look at the pseudo-gapped Kondo model. So that's just instead of having this flat band density of states, pick a density of states that has some power law distribution. So it's absolute magnitude of omega to the power of 4. Okay, so this is now a non-integrable system. And obviously the Hermitian case has been studied back in like the 90s. And there's this phase diagram of this power or versus the coupling J. And what you see below this line is the local moment regime. Above the line is the strong coupling regime. And once you go beyond the power of a half, you can never get back to the strong coupling regime. So this sort of pseudo gap that gets introduced just prevents you from getting back to the strong coupling regime. There's always this local moment. Okay. And now we're going to do the same thing again. We're going to make it non-Hermitian by making J complex. Okay. So then each of these lines here now, as you go down from the blue one, is introducing some dissipation to that J. So you see the line is getting shifted down, and you're also actually going beyond this vertical line at what equals that. So there's one thing I want to focus on, or spending like 10 minutes talking about, we don't have to, is this some representative eigenvalue flow diagram in this region where you're above this red critical line, I'll say, for like a strong dissipation of like 0.5. And what you can actually get is it's not quite the strong coupling regime. We're going to denote the complex strong coupling regime, because what we have is something that looks like the strong coupling fixed point, but with some non-zero imaginary. What we've actually observed is a completely non-Hermitian fixed point in the space diagram. Okay, so in this non-integrable model, this pseudo-gap non-Hermitian Kondo model, what we've uncovered is this like novel complex fixed point, something that hasn't really been seen before in these kind of models. Okay, so it just really demonstrates that the energy method can be thrown at lots of problems. You can solve things that are non-integrable. It can solve things that are general. We can have lots of different 3D models, like an Anderson 3D model or a Kondo 3D model. So with that, I will just summarize what we saw. So I introduced non-Hermitian energy, solved the Kondo model with a full phase diagram way beyond perturbative regimes. I showcased it on this pseudo-gap Kondo model. We solved this non-Hermitian fixed point, and also just advertised it in the paper. We applied it to the actual non-Hermitian Anderson 3D model, the interacting one. I didn't turn off the impurity or anything like that. And if you want to mess around with it yourself, the actual method is on GitHub. Like the code is on GitHub if you want to play with it. You can find the link to that in the paper, which is in the archive, and has recently been sent to URL. Just want to highlight it again. And just to advertise future work, we're working on the dynamical extensions, things to be able to calculate real like dynamical quantities, like Green's functions or special functions or all those kind of things. Okay, so with that, I will finish. Yeah, so any further questions? Did you go through talk? Yeah.
I think you said at some point that you're converging to real energy eigenvalues.
Yeah.
So you also get your Hamiltonian out of your generating, I guess, under the flow. Does that mean that that's flowing to a Hermitian Hamiltonian?
Yes.
Okay.
Because then, I mean, the very last step, like this final like, slice of eigenvalues at the end, that's just the eigenvalues of some Hamiltonian, and obviously if they're real, your Hamiltonian ends up being real in that case.
Is there some physical intuition as to why it should flow to a real something like that?
That's a good question. I'm sure there probably is. I just don't know what it is.
Could it be based on your choice of like how to choose the minimum energy?
Yeah, that could be. I can't think of the top of my head. I thought about that before. This reason why this happens. I guess it's also in the system. I mean, you have this massive bath, and the non-hermiticity is only via this tiny coupling between the spin and the. I mean, if you pick some other way to make this non-Hermitian, like if you made all of these, like in the test case where we threw impurities onto the bath itself, where every single side of the bath had some dissipation, you might not get this emergent fixed point, this emergent Hermitian fixed point. Actually, probably you almost definitely won't, because it's constantly dissipating. It's not just on some impurity coupling. Okay.
So like when the imaginary part of the energy is negative, I guess I can think of that as like the corresponding eigenstate will be damped away and decays away. But when it's positive, then it grows.
Yeah, it's almost like dominating.
Okay, so yeah, okay. I guess I was just wondering about the intuition for that, and like it seems kind of non-physical somehow.
Yeah, I mean, non-Hermitian Hamiltonians are weird, and like their complex eigenvalues are also weird. People like think of them sort of like lifetimes. It's like you're saying, it's like this decay of the eigenvalues in time. But I mean, the norm isn't conserved in like the dynamics, so it's basically like your state can just grow massively into the system. It's almost like gain in the system rather than dissipation. Something that's being pumped into the system, or like enhanced in the system. Okay.
That's going to fill again.